Yeah, they can always interrupt when there's some need for clarification, sure.
Okay, yeah, please. Thank you very much for being here, René, and go ahead.
Thank you, Chris. And also thanks for inviting me to this seminar. It's really an honor for me to talk in that seminar. So yeah, I'm going to talk about exploring large continuous seismograms with machine learning. And the work I'm presenting here is basically my PhD work, which I've been doing in Grenoble in France with Michel Campillo and Léonard Sédot, and also with other collaborators. And since this year, I'm a postdoc at GFZ with Fabrice Couton. And so I divided this talk into 3 parts. So first, I give a bit of motivation, why and how we want to explore continuous seismograms. And then after that, I will present 2 case studies. And one, we will explore urban vibrations during cold temperatures. And in another case, we will explore volcanic vibrations in Kamchatka in Russia. So, and yeah, you can always interrupt me if there's need for clarification, and I will also give you time at each when each point is finished to ask questions. So yeah, why do we want to explore continuous seismograms? Maybe that's an obvious question, but I still want to dive a bit into this motivation here. So what you see here is a continuous seismograms of 20 minutes, and you can see that the seismograms records different types of vibration, which change over time. And if you're a trained seismologist, you might recognize that there are these small signals, which we call earthquakes. And the field of seismology has developed many tools to detect these signals in the continuous data and to analyze them. But as you can see here, that these signals only make a small part of the data, and we don't really know what's going on in the rest of the data here. And so that's why I think it's interesting to explore what is actually in the continuous seismograms behind the signals we know. And also here we have 20 minutes of data, so you can visualize it easily. But now if we have 1 year of data or 10 years of data, the visualization is much more complicated. So we need methods to explore data on a large scale. And also, so because I'm going to talk mainly about urban vibrations and volcanic vibrations, but I know it's like a tectonic seminar, so I also want to give a tectonic motivation here. So yeah, I think like around 20 years ago, the study of Obara discovered the tremors, the tectonic tremor signals in Japan. And that was kind of a discovery by, let's say, by coincidence. And it also shows us it's like worth looking into the continuous data, that there is information here. And we can ask ourselves, how would it be if we would be in 2001 and try to find signals such as like the tectonic tremor? We would know how the signal looked like and what to look for. So there's a similar case in Turkey on the North Anatolian Fault. So the fault ruptured from the east to the west, and it stopped in front of Istanbul. And so there have been studies looking into tectonic tremors happening in that seismic gap there in front of Istanbul, but they reported no results. And so the tools we've developed to look for tectonic tremors are based on the tectonic tremors we've seen in other places, but maybe they can look differently here, or maybe they don't exist. So there are 2 possibilities why there might be no results. And so for that reason, I think it's good to have methods which look into large continuous time series and identify patterns in the data without assuming too much about how these patterns might look like. And so how do we look for these patterns in a, let's say, data-driven fashion? So here again, there's a continuous seismogram, and you can see there are different types of signals again, and without knowing what they are, we can say that, let's say, these 3 signals we see there in blue, they correspond to, or they show the same signal characteristics. Then we have these 2 signals, which also share similar signal characteristics, but they look different to the other 3. And then we could also mark these 6 windows here, and they again show different, look differently. So by comparing these signals in the data, we kind of identify patterns which repeat in time. And when we calculate certain waveform characteristics, we can bring these waveform data into a data space where we can make comparisons, how similar these signals might be to each other. And so the distance in that, let's say, waveform characteristic space tells us something about the similarity. So this is basically the idea of like exploring continuous seismograms in a data-driven fashion. And so, of course, so this falls into the domain of machine learning. And machine learning comes up with many nice jargon, such as features, for example. So these waveform characteristics, that would be called features. So we need to generate good features for measuring the similarity. And the measurement of similarity often happens with clustering. So clustering measures the distance, which estimates the similarity between different signals. And I think the most important part is actually the interpretation later. So the clustering will not tell us what is maybe a tremor or what is a tectonic signal or whatever. It's the interpretation is really crucial, and it's important to have some sort of secondary information from time to time. So, and that idea is, I mean, it's not completely new. I mean, it exists since longer, but I would say like around 2010, we got the computation power to do that on a larger scale. So there's this study from Köhler in 2010 where they looked into continuous seismograms for like 1-2 days. And they used hand design features, something like amplitude ratios, mean frequencies, and so on. And then they used self-organizing maps to identify patterns in the ambient seismic wave field. So then there are many more studies, of course, coming in between, but I just want to outline kind of what was the ideas at the time. So here we started with ideas of basic machine learning. And then also in 2015, there was the study of Ungland et al., which also used self-organizing maps, but as an input, they used spectrograms and not hand design features. And they used that to explore volcanic tremor signals. And then I think, so there are many unsupervised deep learning methods nowadays, I would say. So we went from machine learning to deep learning, and I just want to mention this, like this unsupervised deep embedded clustering, which have been used by a couple of authors already. And what happens there is that the clustering gets optimized together with an autoencoder, and it has been applied to volcanic environments, urban and glacial environments, and so on. So what I want to focus on in particular here in this talk is, let's say, a method which comes out of this paper from Leonard, Sedo, and colleagues in 2020. So I would say what is kind of unique in that study is that they replaced these hand design features, all the spectrograms, with a scattering network. And then they use that scattering network also in an end-to-end unsupervised learning framework where they learn the wavelets inside the scattering network and the clustering outcome. And they use that to pick up a precursor signal prior to a landslide. So now, what is a scattering network? Yeah, it will be hard to explain everything what happens there, but I try to give you a good picture in a couple of minutes. So I think you can summarize it with like one phrase, that it's like a non-learnable convolutional neural net with wavelets instead of neurons. And this is how it looks like. So at the top, you have the 3-component seismogram, which it doesn't matter if this is 3 or 1 component. But so we take sliding window, and for each sliding window, we do a wavelet convolution and extract scalograms. Then from the scaleogram, we perform a pooling operation for each frequency bin. This can be max pooling or mean pooling, and we retrieve what we call scattering coefficients. And these are the first order scattering coefficients. What then happens is that we take one frequency bin, and we do a second set of wavelet convolutions, and we get a second order scaleogram. So we get an image out of a line here. And so we do this for each line in that image in this first order scaleogram. Here we do the same, we do a pooling operation. And then we collect these coefficients at each layer and save them into a scattering coefficient matrix, where we have the first and second order scattering coefficients for the east, north, and vertical component. And so maybe what's also different to a convolutional neural net is that here you extract information at each layer, while for the CNN, you only extract information at the very end. So, and what Leonard did in the first study is they learned these wavelets. But what I'm going to show you is that we don't learn them anymore, but we fix them to GABA wavelets or any wavelets you want to have. So that's how it works, basically. And what's so interesting about these scattering coefficients? How do they compare to other representations? So first of all, they're translation invariant. So that means if you have a signal inside your moving window, doesn't matter if the signal is at the end or in the front, the representation is always the same. And that's the same for hand design features, and also if we use spectral features. Then the choice of hyperparameters. So what kind of wavelets do we take? What is the frequency support of the wavelets? How many wavelets? It's kind of driven by the data we have at hand and the task we want to solve. So the choice of, let's say, hyperparameters is a bit more intuitive than for conventional CNNs. Then, so this scattering network was firstly introduced in this paper of Andin Mallah in 2014. So Stefan Mallah, he is kind of he was driving a lot this scattering network and scattering coefficients, but for audio classification tasks. And so in that paper, they also argue that the good thing about these scattering coefficients is that if you have a small change in the signal, so let's say you have an earthquake and you have a little time warping because of change of position or faulting mechanism, then the change is also small in the scattering coefficient space. And for spectral coefficients based on the Fourier transform, this is not true. Like you have higher changes in the higher frequencies. So it's not so stable to small time deformation, the spectral coefficients, while the scattering coefficients are supposed to be more stable. Then I think what's also interesting, it's like kind of a compromise between like, we keep some interpretability compared to CNNs, though spectral coefficients are much easier to interpret. And at the same time, we have some sort of like high level data representation. So it's better than a spectral coefficients, but of course, if you can learn the task, this performs much better than in that case. So yeah, exactly. Depending on the task, it might be better or worse. And yeah, something to say about the interpretation. So the first order coefficients, they actually kind of resemble the amplitude spectrogram. And the second order coefficients, they contain information about modulation and shape of the signal. So let's say if you have an earthquake and you have a P and S wave, so the time difference between P and S would be stored in the second order coefficients here. And so there's something about let's say, the small history of the scattering network in seismology. So as I mentioned earlier, so Leonard kind of introduced that into seismology in this 2020 paper, where they learned the wavelets and they optimized Gaussian mixture models. That was also the time when I joined as a PhD student in Grenoble, and we kind of decided that we don't want to learn the wavelets anymore for multiple reasons, but that we directly we set the wavelets to GABA wavelets, for example, get the scattering coefficient matrix, and then do data exploration, such as like providing a hierarchical overview with hierarchical clustering of the data, or doing something like what we call seismogram atlases. So this is not an end-to-end unsupervised learning framework anymore. So we changed it from this end-to-end framework to really like data exploration. So that was the first part about like a bit the methodology and so on. So if you have any question about, or if something is unclear, you can ask questions. Okay, if not, I would continue. So yeah, so in the first part, so that's the map you see here. It's the city of Hamburg, where I did my master's degree. And while I did my master's degree there, we installed these broadband seismometers in the city of Hamburg. And we installed at a meteorological measuring site. So it was a cooperation between, let's say, climate science and seismology, because we wanted to infer new ways to monitor the critical zone in an urban environment in times of climate change. So we have these 3 broadband stations, and then we also have some other sensors in the air and in the ground, which measure temperature and the water content. And so that was the original idea, to kind of track what's going on in the critical zone. And what we have around is like different parts of, or the different types of seismic noise, let's say. So we have like a lot of industry located over here. There's a gravel pit really close by. Then there's a highway passing along here and a metro line. And what was surprising, what we find in the data is, so the winter of 2018 was really cold. So here you have time series data from January to April 2018. And in black, you see the relative velocity variation retrieved from the ambient seismic noise cross correlations. Why the axis here is flipped. So we have like velocity increases and decreases. And then we have the temperature in red, which was measured at the surface. And in blue, it's directly below the surface, just a few centimeters. And what you see is that we have this cold temperatures in February when we have also increasing velocity changes. And so what we kind of interpret here is that when the ground freezes, just like a few centimeters, we have a velocity increase. And then when the ground thaws again, we have a velocity decrease. And so that was work done. So this has nothing to do yet with the scattering network. So this is about like, okay, we saw that the surface wave velocity got changed due to the freezing.
René, it's Chris. I'm sorry, I think I missed this, but how many stations are involved here? Is it one station or a little network? Or?
It's 3 broadband stations.
3 stations. And the way you're plotting it, the velocity is increasing down?
Why I do that?
The plot for the velocity increases when the black line goes down?
Exactly, yes, yeah. So I switched the y-axis to align it better with the temperature.
Gotcha, thanks.
Yeah. And so yes, so that was something we knew. So this is what we got from the data. And so now then I went to Grenoble, to France. I worked on this on these unsupervised learning frameworks. And then we got the scattering network, hierarchical clustering, and so on. And then I was kind of curious, like, can we identify this directly in the continuous seismograms without doing the ambient seismic cross correlations where you have to widen the data and you like, here we have 3 stations involved, 3 component data. Can we directly infer it from the raw continuous seismograms without doing all the pre-processing? So it was just a curiosity thing at that moment. And so I started the machinery. I calculated the first order scattering, or I calculated the scattering coefficients, but what I'm showing here are the first order scattering coefficients of the east component. So maybe you remember I said earlier, it looks like a spectrogram, and that's what you see here too. Like you have the frequency and the time axis, and you can see these fringes due to day and night and week and weekend. And so we fed these scattering coefficient matrix, not only the east component, but like the whole thing, into an independent component analysis to retrieve more than like that's what we call like features. And so how we interpret them is like that these are our data-driven waveform characteristics. So you remember that we want to find good waveform characteristics to do the clustering task. And so these are the waveform characteristics, which don't give us a lot of information if we look at them like that. So again, here's the time axis. And now we put that into a hierarchical clustering framework. And we get this dendrogram. So at the top, all our data points belong to one cluster, and then we start dividing the clusters into subclusters. And so now the task is there any cluster in here or branch in that tree which correlates in time with the ground frost? And so we retrieve these 5 clusters, A, B, C, D, and E. So at each layer, you can retrieve a clustering solution from the dendrogram. And when we now look at this, what we call like a normalized cumulative detection curve, so how these clusters detect something in time, but normalized to 1, you see there's this one cluster, D, which correlates quite well with the time of freezing, while the other clusters detect more continuously in time. So basically, that's task solved. Cluster D is the ground frost. But so there's more coming to it. So we also want to know what's the rest and what is exactly the imprint. So to understand what is the rest, so we know we are in an urban environment, so it makes sense to look like how do these clusters detect over the course of a day, and how do these clusters detect over the course of a week? So if we take cluster A, we see that if we look at the histogram over a day, it goes from 6 to 6, while we have a kind of a break at 9 and 12, which corresponds to breakfast and lunch break time in Germany. Then also it detects from Monday to, let's say, Friday, a bit less detections on Friday, and nothing on Sunday or Saturday. So of course we didn't locate it, but like just based on this, we would say that cluster A has something to do probably with the gravel pit nearby, where we know that people make lunch break, they make breakfast, they don't work at the weekends. Then cluster B has kind of a similar time distribution. It goes like, let's say, from 6 to 6, but it's less less constrained, and it also doesn't have the breakfast and lunch break. For the week, it's also from Monday to Friday with a few detections on Sunday. So this might be also related to some urban activity, which is mainly active from Monday to Friday. So for sure it's not the metro line, and for sure it's not the highway, but what exactly it is, we don't know at that point. Cluster C has a very particular distribution over the day, with less detections in the morning and in the afternoon, and it detects all days from Monday to Sunday. Just looking at this, we don't know what it is. We need more information. We would need to look at the waveform characteristics, at the spectral features, and then we might know what it is, but only with that information, we cannot say what that might be. Cluster D is our ground frost, and now we see that we detect also more during the night, which maybe makes sense because we have colder temperatures during the night, but also a bit more during the weekend. So that doesn't make much sense to detect more ground frost at the weekend than during the week. And then we have cluster E, which has the similar distribution, more during the night and more at the weekend. And so we interpret that cluster with, let's say, the ambient seismic noise, where we don't have much urban activity happening. And so cluster E tells us also something about cluster D, that so if that is the ambient seismic noise cluster, that one has the same temporal signature in some way, just that it only occurs during ground frost. So this tells us that probably cluster D is the ambient seismic noise, which is altered by the occurrence of ground frost. So that the ground frost itself is not initiating a new signal, but it's altering existing signals. And so if we put them back together, so if we merge cluster D and E and go back to that branch here, we can now also see that we have a continuous detection, and you can see like these little like increases, and then it's flat again, then it increases again. So this is the day and night cycle you see very slightly on the cumulative detection curve. So yes, if we have the ambient seismic noise, which is altered by the ground frost, that tells us that probably there's also other signals which must be altered by the ground frost, such as the gravel pit or the urban cluster. And it's true, like if we go into cluster B and we go a bit lower, like we take that branch here or that branch, we get a subcluster of B, which correlates also in time with the ground frost. So that tells us, yes, we also have urban vibrations, which are now altered by the ground frost, not only the ambient seismic noise. So we detected clusters of which correlate in time with the ground frost, which tells us there is information in the continuous seismogram. But until now, we don't know yet what is exactly the imprint. And so this is the task you want to solve now. So for that, we take cluster D and look at its location in the feature space. So, and that is the centroid of cluster D. And we can see that we have very high values for feature 15. And when we look at feature 15, you remember we had this matrix here where we had the feature index here and the time here. And if you look at feature 15, we can see that in time it correlates super well with the temperature. So this is kind of like a data-driven feature which tracks the freezing and thawing as we saw for the dV over V. Like it looks very similar here. Also that we have a stronger increase during the second time than before. So we have a feature identified. And now what we can do is we can go back to the scattering coefficient space. So these are the original scattering coefficients for the east, north, and vertical component. And you see these day and night fringes. And so this is the first order component. I'm not showing the second order component, which would be too much to show here. But what we can do now is that we take these features, and what ICA is doing, it's doing like a matrix factorization. So we can take our feature, which is tracking the freezing. We can go into this like, okay, it's written projection matrix, but for ICA, usually there's the term mixing matrix. And we can go back and reconstruct partially the scattering coefficient matrix with that one feature. And so maybe something to make a comparison with is that ICA and also PCA, which is principal component analysis, have been used a lot for facial recognition tasks. And so the difference for you who are familiar with PCA, the difference between PCA and ICA is that ICA is able to identify parts like, let's say, certain parts in the face, such as the eyelashes or the eyebrows or part of the mouth, while PCA kind of sees always the global pictures in these images. And so this is what we're going to do now, that we go back into the scattering coefficient matrix to see what is highlighted there. Why do we have the freezing imprint here? And so when we go back, we firstly see that we remove completely this day and night cycle. And what we see now is that we have something going on at the two horizontal components, like that there is some sort of like amplitude decrease here and here, which is not so strong on the vertical component. So we can see that the amplitudes decrease mainly on the horizontal components, and we did then some modeling to understand what's going on. And it's actually what's happening when you freeze the very surface of the when you freeze the very surface, you change the modal energy of the surface waves so that you kind of suppress the fundamental mode and you go to higher modes. And so this is basically the imprint we see here and why we have the amplitude decrease on the horizontal components. So to summarize, what actually happened is that we were here in the dendrogram, we identified multiple clusters which were correlating with the freezing effect. We then asked ourselves, what is exactly the imprint? We went back to the feature space. We identified the feature there, which tracked the freezing. And then we went back to the scattering coefficient space to understand what is the imprint through the partial reconstruction. And so, yes, so I already mentioned that it has an impact on the higher modes. And so that actually goes back maybe to the dV over V measurements, because now the question is like, what is actually the impact on dV over V measurements if we, I guess if we go large, far enough into the coda, it doesn't have a strong impact. But we basically maybe also change the occurrence of surface wave modes inside the ambient seismic cross correlation. So that is about it for the Hamburg case. Now I would go on to volcanic vibrations. If you have any question at that point, you can unmute yourself. I don't see the chat, so if you have questions, just ask.
May I ask?
Sure.
Yeah, thanks, René, for the talk. I think I just missed the part where you explained why there is a change in horizontal components, but not in vertical.
Oops, let me go back. So through the partial reconstruction, we can see here, like very slightly. So we remove these day and night fringes. And so I don't plot the freezing time here, but when it freezes, it's basically around here and here. And what we see is that we have this very slight decreases here on the east and north component, but we don't see it so much on the vertical component. Does that make sense?
Yes. Is there any explanation that why this happened only on horizontal component? I mean, the interpretation out of this.
So so we did the modeling of surface wave modes, and we saw that when you introduce a high velocity layer at the surface, you kind of suppress the fundamental mode and you go to higher modes. And that's the reason why we have this change in horizontal to vertical ratio, basically.
Thank you.
So maybe something to mention, like if you would do the HOV ratio of the original data, you wouldn't see much because you have so much going on due to changes in the seismic sources. But if you would do that now HOV on this, you would see much better that there is a change in the HOV ratio, which comes from the surface wave mode changes.
Thanks.
So I have a question, and I raised my hand just because maybe other people would like to put themselves in order to ask questions. Yes, so maybe I have a follow-up question that was independent too, which is that one can imagine that the freezing gets deeper and deeper throughout the winter. So do you see that signal, or do you really just see freeze and thaw?
Yeah, no, so Hamburg is not really like it's located close to the coast. So so here we have at maximum we have 5 centimeter ground frost. And it didn't get deeper than that. So but I think it would be interesting to see what's going on for permafrost studies. So actually I was thinking about this, like what is the impact now for permafrost studies? Because I also know people do DV over like these velocity variation measurements on permafrost studies. And I guess if you go far into the coda and if you're in a good frequency range, you're not affected by the changes of surface wave modes. But I guess, yeah, maybe we need to be careful if we do velocity variation measurements when we know that the surface is freezing. And then if it goes deeper, it's a good question. I don't know what's gonna happen, because here what is happening is you kind of change the boundary condition, right? But if you go deeper and deeper, then you change the whole medium.
Yeah. No, it's an interesting thing to look at, but yeah, really cool. Thank you.
Thank you.
Go ahead, Zohar.
Hi. I have a
Hi.
question. I don't know if I didn't understand, or I just wanted to clarify. How is the traits of similarity that you find between waveforms different than using cross correlation?
You mean the difference between doing ambient seismic cross correlation and using the continuous seismogram?
Then using the I don't know how to phrase it. Okay, well, I'll rephrase it and I'll come back. Okay.
Sure, like you can also write it down and we answer it later if you want.
I mean, you use like a certain AI, right, to find the similarities.
Well, so let's say the AI I'm using here is hierarchical clustering and maybe ICA. So it's like very basic machine learning, but there's no deep learning happening or anything. There's no, yeah, so the hierarchical clustering kind of finds the clusters in the feature space. And this feature space comes from this independent component analysis, which is a statistical model. And what we feed into the statistical model are these scattering coefficients, which are based on wavelet transforms, or like a cascade of wavelet transform. I don't know if that answered your question.
Yeah, it did. Okay.
Okay.
Thank you.
Thank you. Okay, so then I would go back to the third part now. Yeah, there we are. Okay, so yeah, so we move away from Hamburg. We are going to a much colder place, to the Kamchatka Peninsula in Russia. And so the Kamchatka Peninsula in Russia, you can see it over here. It's located on the far east side of Russia at the Pacific Ocean. And here we also have a subduction zone and many, many volcanoes. And there's also the Kliuchevska volcanic group in here. And so the Kliuchevska volcanic group, there was an interesting experiment in 2015-16, which is called the KIST experiment. And so basically, it was a French, German, Russian collaboration with Nikolai Shapiro and other colleagues who installed broadband seismometers in short period instruments around this volcanic group here. And that data was used by another PhD student he was a PhD student in Grenoble, Cyril Jonot, and he used the data to detect tremor signals with that network and to locate them. So these tremor signals are these black spots you see here. And this orange triangle is this Kliuchevskoye volcano. And I marked also a few broadband stations around it. And so now we took the broadband station, which is located the closest to the Kliuchevskoye volcano, SV13, and we calculate the first, and now I show the second order coefficients also. So we calculate first and second order coefficients from the east component. So here it's similar again to the spectrogram. We have the time frequency, and yeah, the second order, if you look at it like that, you don't get a lot of information. But you can see we have like varying amplitudes in time. And this is the tremor catalog from Cyril in time and depth. And you can see that we have these amplitude increases when we have basically a lot of tremors at shallow and deep depth. And then we also have some deeper tremors in the beginning of the recording time. So this spans a whole year from summer 2015 to summer 2016. And then we have also more information. We have something about the alert level of these volcanoes and the time average discharge rate estimated from satellite data. And so what we see here actually is like, so we have like 2 reactivations of the Atlantic system, we could say. We have an eruption happening around April, like the exact time is not really clear, but the orange color corresponds to eruption. And then we also have an explosion, which is this red little dot here at the end. So this is what we know what happened, and this is the continuous seismogram from that station close to the volcano. And so now we feed that data into independent component analysis again. So maybe also something to say why we did that. So we were kind of motivated by this study from Hamburg that we could identify this medium process in the continuous seismogram. So we're thinking, okay, close to volcanoes, we have a lot of stuff happening. So maybe it's possible to separate different types of sources, medium changes, whatever we find in the data. And maybe you're also familiar with the term volcanic tremor, which can have a lot of different signal characteristics and a lot of different sources. So we took this coefficient matrix for all 3 components, and we feed it into 3 different ICA models because we also want to investigate the impact of a changing number of components. So we went for 4, 12, and 50 components. So depending on the number, you get a different result. And so these are the 3 different models. And here you also have the tremor count in the gray histogram. And so what we see is that if we keep increasing the number of components, we go towards something where we have some sort of like a diagonal line in time and let's say feature index here. And so what does that mean? So what are these saturated colors we see for the independent components? So each feature or independent component represents some sort of pattern in the continuous data. And so when we have a dark blue or dark red color, it means that that pattern is very active. So this tells us that, oh, okay, that pattern is very active, then it stops, and we have a new pattern which is active, and that stops, and a new pattern. And so this diagonal line, it tells us basically that we have an ever-changing volcanic, or ever-changing wave field, and it never looks the same throughout the recording time. And so we were a bit surprised to see that. We were wondering if that is due to the presence of the volcano, or maybe that's a usual characteristic of seismic time series. So in that map, you see also other broadband stations like ER18, 12, SV7, and so on. And they all have an increasing distance to the volcano and to the center of the tremors. And so now we do an ICA model for each of these stations with 50 components. And what you can see is that this diagonal line kind of vanishes with increasing distance. So it means that, okay, this diagonal line is not a usual thing in seismic data. It has something to do with the presence of the volcano or the presence of these tremor sources. what is also interesting that if you're at that station or 18, so it's down here, it's like more than 60 kilometers away, you can see some saturated colors when we have a high tremor count, like at that time, and also at that time or here. And that corresponds also to kind of the reactivation of the plumping system, which happened here, and then we have the eruption. But we see that if we're close enough, we see the continuous line, this diagonal continuously. So now the question is, how can we relate it to something physical? What's going on in the data? What are the patterns here? And so for that, I'm gonna introduce something to you, which is called uniform manifold approximation and projection. So it kind of does the same task as what we did with ICA. So with ICA, we wanted to reduce the dimension, but we could see that we need 50 dimensions to see the diagonal line, and 50 dimensions is too large to interpret what's going on in each dimension. What are these different features? So what we decided to do is going for a manifold learning technique to overcome these limitations. So to kind of visualize what's going on. So there's a lot of stuff happening in UMAP, but this is just an example, like, well, what is it actually doing? So that's the MNIST data set where you have these handwritten digits. And so if you vectorize each digit and you feed it into the principal component analysis, and you ask for 2 components, this is what you get. And so now each color represents 1 digit, so a 0, a 1, or a 2. And you can see that, yes, there is some sort of separation between these different digits, but at the same time, there's not really a spatial separation, like there's an overlap. And that is because PCA preserves pairwise distances, but that it does that at the cost of losing information on a local scale in the high dimensional data space. So now there's another manifold learning technique called TSNE. Maybe some people are familiar with that. So what you can see now is that these different digits are much better separated. Like we have no overlap of different colors, but at the same time, we have some sort of artificial structure. So for example, here, I think that's the number 1. You can see you have little clusters inside the number 1, which are not real structures in the data, but it's kind of artificially created by TSNE. So these manifold learning techniques, they preserve better the local structure. So that's why you can separate now these digits, but you lose some information on a global scale, and you also distort distances and the density information a bit. So that's a bit the price you pay here. And UMAP, I would say, is kind of similar, though there's the general notion that it performs a bit better than TSNE at preserving the global structure, and it also runs faster than TSNE. And it's also more stable towards its hyperparameters. So that's why now we're gonna go for UMAP to reduce this scattering coefficient matrix from the different stations. And yeah, so that's what we do. We take the scattering coefficient matrix, and now instead of feeding it into the ICA algorithm, we feed it into the UMAP. And so these are the 2-dimensional representations we get for the 6 stations. So what you see here is like, so you have the UMAP variable on both axes, and you have data points in this UMAP space. And so these data points are color-coded with its timestamp. And so you have 2 data points which are close in that space. It means they are similar. And if they're far away, it means they're dissimilar, the underlying seismograms. And what we can see now is that we have this color gradient for the station SV13, which is very close to the volcano, which tells us, okay, the time is again kind of encoded in this in this continuous seismogram. So no matter where we move in this space, there's always a different time. This is also true for these 2 stations. But then if we go for stations further away, we see we have overlapping colors. So that means we have repeating patterns, or it's a bit more, let's say, random. So it confirms what we have seen with the ICA model. So that already tells us, okay, UMAP is not doing something completely new here. So both methods confirm the same observation. Yeah, let me go back because the video directly starts to play. So I'm gonna play the a video of that station and that station of the UMAP spaces. And so the video will kind of paint the colors or the data points in time. So you see better the temporal evolution, what I'm talking about. So this is the station close to the volcano, that's far away. And we have the tremor catalog here and the discharge rate of the volcano. And you can see that now there's not much tremor activity happening. It's kind of random sampling the space here. And then the tremor sets on and it starts to follow these linear structures. Sometimes it stays at some spot, but then it continues to be a bit curvy, again, linear, goes back into the noise, let's say, and then it starts again, and it explores a new space in this map here. And so it continues, and it's very different to what we see over here. It keeps painting on the same spot, basically. So we really have an ever-changing wave field close to the volcano. And so now, yes, how can we relate these different areas in the UMAP space to different volcanic activity? So remember, we have been in this ICA space. We have seen that diagonal line. It was too many features to understand what's going on. So we went for UMAP to bring it down to 2 dimensions. And now we can kind of easily relate maybe different areas here to what's going on in the volcano. And so we use the secondary information we have, such as the time average discharge rate, to, for example, identify, oh, over here we have the eruptive activity. Then we have the tremor catalog, and we can separate between deep and shallow tremors. And we can identify different areas of where we have deep and shallow activity. And for example, over here, together with the time information, we know that this is the period where we have the early deep tremors before the reactivation of the plumping system happens. Then we can also pick some random data points and look at the underlying signal to better understand what's happening. So to also have some, let's say, some ground truth of the signal. So to look at something we are familiar with. And so, for example, if we look at some data points from the early deep tremor activity, we see these spectrograms. So I'm just showing the east component here. So they are basically the tremor signals coming corresponding to the deep tremor, and we can see they kind of look similar compared to what's coming over here. So that's why they're also close by. Then in orange, this is kind of the first reactivation. So we have, you might remember from the video that suddenly it makes a jump out of the noise over here. So that is when the first reactivation of the plumping system happens. And we start to see an increase of the amplitude and also a changing frequency content. So that's why it starts to travel in the space. And it continues to travel until it reaches that area over here. And we can relate that to mainly shallow activity. And we start to see some sort of transient signal overlying the continuous background activity. So over here and here, that was like more like a continuous tremor signal. And then we slowly start to go into something which has some transient character also. And these repeating transient events, you can see they also change their interval times and their frequency content. And so we can continue to interpret each step by step. But so basically, this is the synthesis of the. So yeah, I haven't said the name yet, but we call that like a seismogram atlas, because UMAPs have been used also in other data-intensive sciences, and often they term this atlas as like a metagenomic atlas, activation atlas. So that's why we went for seismogram atlas. And so what you see here is the synthesis of the atlas together with the secondary information to relate different areas to different activities. So I mentioned already, so here over there, we have mainly the early deep tremor activity. Number 3 and 8 mark the points of the reactivation of the plumping system, which also come along with a jump inside that atlas. So it doesn't, like when we have the reactivation, there's no continuous traveling, but it jumps to another place in that atlas. Here in 7, I think that's also interesting. So that was the noise we had before the reactivation. And then that is kind of the noise we have after the reactivation. And for some reason, it doesn't overlap. I mean, there could be many reasons for that. but I think it's interesting to see that we go from the tremor activity, there's a continuous traveling into that, let's say, noise, stays here for a while, and then it comes out again. And I would say from the catalog, we don't see that behavior, that there's this very slow tremor stop and also reactivation, which is very different to the reactivation of the whole plumping system we saw up here. Then also 11 and 15, this is when the eruption happens, like it occurs, and also the explosion. So they are located nearby. That makes sense. Both are probably high amplitude events with a lot of energy. And then here in 14, we have the co-eruptive tremor, where we don't really have any significant pattern changes. It kind of stays in that island, and it doesn't travel around anymore, as we have seen before. Yeah, so that is also now on the archive for the AGU journals, still under review. And yeah, with that, I would come to the end of my talk. So to give you a few takeaway messages, because there has been a lot of information, I hope I could show you that continuous seismograms, they contain a lot of information. And I guess that's true for any context. Doesn't matter if it's an urban context, volcanic, tectonic, glacial. There's always something to explore, I would say. Then I think also, I hope I could convince you that these scattering coefficients are useful data representation. But I have to say, we need a better understanding of what's happening with the second order coefficients. So often I showed you first order coefficients. So the second order coefficients, they go into the algorithms, but they are very hard to interpret. And I hope that there's something to do to increase the interpretation of the second order coefficients. And then I think these atlases, what I really like about them is that they're an interesting way to perceive from time series. So that was, I showed you 1 year of a continuous seismogram. And I think what we usually do is like we look at either the seismic time series or we look at a spectrogram. But I think what I like about the atlas is that you kind of see when do we have repeating patterns? Is it a bit different? Is it very different? So here it was like one eruption cycle. But I think it would be interesting to look at decades of volcanic data to see like what happens if there are multiple eruptions happening and so on. And the last thing I want to tell you is that, so if you're interested in that, like also into the methodology and so on, Leo and I, we wrote this Python package called ScatSizeNet. And so the core of that package is the scattering transform, and it gives you the scattering coefficients from the seismograms. But then there are also many tutorials about like data exploration tasks. So doing dimension reduction, clustering, these atlases. Yeah, so if you want to have a look at this too, just to let you know that there is a package and there are tutorials for that too. And yeah, I'm ready to take any questions if you have any. Thank you.
Thanks very much, René. That was such an interesting talk. I will invite everyone to unmute for a minute, turn your camera on, and join me in thanking René for a great talk. Thank you.
Thank you.
Yeah, really interesting. So easiest thing to do is to use the reaction button at the bottom of your screen to put ourselves in some order to ask questions, and Paul Johnson is going to go first.
Sorry, René, thanks so much for the talk. It was super interesting.
Thank you.
And I have I guess I have a couple comments. I think you've shown us an example or two examples where clustering was incredibly powerful, providing information, super rich information that we wouldn't have obtained probably in any other manner, and that's the volcano. In the case of the Hamburg study, it seems to me that it's useful, but perhaps less useful than doing something supervised. If you had used, for example, some sort of machine learning, not necessarily deep learning, but something that allowed you to extract the features, you might have done just as well or even better. And the problem with clustering, of course, is making decisions about the number of clusters. So that's just an observation and a comment. Any thoughts on sort of that general comment?
Yes. So I mean, I agree. Like I think if you have a task where you have a label, you have the temperature time series. So it's true, you can do like supervised learning, and it's also something we did. But it was a bit, well, so there are two things. So one thing is, I think the supervised learning, it also worked interestingly well, but it depended on what we did. So we did like some sort of regression models. And when we were shuffling the data, it was doing fine. But if we would divide the data in two different like training and test set, and we would separate it in time, it would not work anymore. Let's say if we would train it on the first freezing period and we would test it on the second freezing period, there would be difficulties, maybe because new sources would have appeared. So the thing is, the problem with the supervised learning, I think, is a bit in that case that the conditions, the boundary conditions keep changing. So there's not only the freezing, but maybe there are different sources appearing. Maybe the water content changes too, which has not been sampled by the training phase. But it's an interesting idea, and I think so. We tried that. It seemed to work, but it only worked when we shuffled the data. And I think then also, of course, from there you could also go to like identify the important features to understand what's going on. So that's because what we also wanted to know is like, what is the imprint?
Exactly. You hadn't mentioned that you'd done supervised learning, and I think it's an important observation to say that it didn't work. I mean, you have what you described as non-stationarity, right? Sort of one of the biggest hurdles we face in geoscience is applying machine learning. So in that case, clustering does make much more sense, and I think it makes it clear why you went down this path. So that was really helpful for me. The really interesting aspects about the volcano are just the maps. What do you call your maps? The
Seismogram atlas.
Your atlases. I mean, it's just remarkable how the patterns you're seeing in these, and what it all means is an enormous challenge to come up with. The interpretation is very challenging, but at the same time, you have a starting point, which we didn't have before. So, yes, bravo, super interesting.
Say it again.
Really, really interesting, René.
Thank you. Maybe something also to mention to that comment. So yes, I totally agree with you that interpretation, it's really always the most difficult part in that work, that you get your clustering results, you get your dimensionality reduction results, but then making sense of what you see. And I think what is interesting for that volcanic time series is that really what is this linear structure. So I have done the same atlas, or I've done also an atlas then for the Hamburg case. And for Hamburg, it looks completely different. Then it's like kind of going back to the same things, because it's like day, night, week, weekend, and then the freezing. So it repeats its pattern. But here, the volcano, it's really, it always it travels into a new area, and it travels often along a line. And sometimes it makes sudden jumps, which then I guess we interpret it as like sudden signal changes. But then also to make sense of all of it, it's, yeah, I think if we would take 10 years, then it would be much more work too.
Paul, you would follow up on last time?
I was just wondering, René, if you could relate any of the pattern analysis, the atlas, to, for example, eruption, and you're actually saying that in your bullets on the right. And so I guess what you've done is quite a bit of interpretation already, and there's much more to do. Is that correct?
Yes, there's much more to do, exactly. So I think one first thing to do would be like to scale it up to more eruption cycles, to see if maybe we go back to the same spot. Are we taking the same path if it's going towards the eruption? So the eruption is happening here, but what happens before is that we travel along that line. There's this gap, and we come from here. So actually what happens is that we come out of this noise, then we have the reactivation of the plumping system, and then it jumps back to here, and then it starts traveling until the eruption, and then it goes along that way. I mean, yeah, there's in the video, it's much better to see. Like, so I looked so much at the data, I can tell you what is happening, but yeah.
Yeah, it'd be interesting to see if these patterns repeat, and that's what you're saying. So
Yeah.
you need more data.
Yeah, exactly. More data. Yes. Yeah. And yeah, I also wonder if there's any way to help with interpretation, then also like to maybe also do some density-based clustering on the atlases. I think that could be another way to help identifying areas of common or repeating patterns.
Great. Thanks so much, René.
Thank you.
Zara, please go ahead, Zara.
Thanks again, René, for the great talk. I have two questions. First is related to first part of your talk. When you were comparing scattering network and deep learning, am I correct that when we use scattering network, we have some scattering coefficients that we know them, or kind of we have sense out of them, so the interpretation would be easier? But when we use deep learning, we may capture more information from the waveform, but then the interpretation is more difficult because we don't have sense of those features.
Yeah, I mean, okay, that's the general, maybe that's also more an opinion than effect, but I guess, I think there are also ways to interpret learned networks, but I guess when you go for more complex deep learning algorithms, you know less what's happening. I guess the most famous example is kind of like if you would use a transformer and scale it up with many layers. I think then it's really hard to understand what did the transformer see in the data. Though it works, like you can also do interpretation with that. Though I think here with the scattering coefficients, because it's based on wavelet transforms, so that's why I would say like there is more intuitive understanding what they are. And so the second order coefficients, they relate to the shape and modulation of the signal. And this is also something we see from time to time, but still sometimes it's hard to really understand what happened there. So I mean, there's also the difficulty sometimes to interpret the second order coefficients, but I would say for seismologists coming from this time frequency background, I find a scattering network more intuitive than deep learning methods.
Yeah, thanks. And is there any specific reason that you used hierarchical clustering and dendrogram?
Yeah, so before going for the hierarchical clustering, Leo did this Gaussian mixture model, and he learned the Gaussian mixture models. And so with the hierarchical clustering, you get that we moved to the to hierarchical clustering because you get the dendrogram. And for me, the dendrogram is a bit similar to this atlas thing, that you can use the tree to understand how your data splits and merges. So you have also a notion of what are these what are these branches meaning in the dendrogram, and that's why we went for hierarchical clustering, to not make a decision for the number of clusters, basically.
Thank you.
Thank you.
And as we go to Menendrine, just encourage, especially early career people, to raise your hand and join the discussion. Menendrine.
Thank you. Super interesting talk, and I love the visualizations as well. I'm not 100% sure if I remember correctly. Do you use the these wavelets? Are they also the input for the UMAPs, or was this only for the first part?
Yeah, no, the scattering coefficients. They are the input for the UMAP. Yes.
Okay. And at some point you said that you fixed them. That I think you started off with learned ones, and then you fixed them to something that is not being learned. Is that? Can you elaborate a bit on that and say?
Yeah, I'm going.
Why fixed ones work better?
Yeah. So it's that basically. Yeah. So first, there was the idea of learning the wavelets. So that you initiate the GABA wavelet, for example, and then you learn it with optimizing the clustering results. So in that way, it's very similar to the deep embedded clustering. So, but instead of having an autoencoder, you learn the wavelets of the scattering network. And why we kind of neglected that is that we saw for other applications, it's not true for all the applications, I would say, but for the applications we tried, we saw that without learning, let's say in the first epoch, you already have meaningful results. And